Good afternoon, everyone. My name is Nantongo Jocelyn Madrin, and I'm here to talk about the introduction to machine learning. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. As we look at the diagram here, these are the steps we use when we are going to carry out machine learning. We start with data. Here we are going to collect data from various areas around the world. You can specify to collect data about health, about anything you want. When you get that data, you're going to train the machine to be able to perform or to adhere to that data. So in training the machine, you're training the machine to learn the patterns from the data. When we go to building the model, you're building the model to implement the project and also implement the model of the data. After that, you're going to predict the outcome. In predicting the outcome, the model is used to make predictions. See how you use the model to make predictions of the outcome. Yes, when we continue, we go to the types of machine learning, and those are two. That is the supervised machine learning and unsupervised machine learning. For supervised machine learning, it involves learning from labeled data sets, and then for unsupervised machine learning, it involves learning from find the patterns or structure in the data, such as clustering or dimensionality reduction. Yes. When we continue, we are going to look at a data model. And a data model is a representation of some phenomenon. It is a representation of some phenomenon. And in a layman's language, you can say that it is a simplified representation of something complex. Like you can think of a map that can help you navigate to a city. So there are types of models. That's a deterministic model and probabilistic model. A deterministic model is discrete and a probabilistic model is continuous. A deterministic model, there is no randomness. So these models work with fixed and exact relationships between inputs and outputs without any randomness. And probabilistic models, there is randomness. These models acknowledge uncertainty and randomness using probabilistic functions to make predictions. And we have types of probabilistic models. Those are regression models, correlation models, and parametric models. When we continue, we go to look at regression models. On the next slide, there's regression models. Remember that probabilistic these are used to represent the relationship between one dependent variable and explanatory variable. So these models are a type of supervised learning algorithm used to predict continuous outcomes. And the goal is to establish a relationship between independent variables and a dependent variable. As we continue, we have the regression steps, and they include as you've seen them, they include hypothesized deterministic components, specify the probability distribution of random error team, evaluate the fitted model, use model for prediction and estimation. And there are also different methods of regression models. That's linear regression. And for when we talk about linear regression, this assumes a normal distribution of the residues. And when we continue to the next slide, we're going to talk about parametric models. A parametric model is a model where you know which model exactly you fit to the data. And a non-parametric model, here the data tells you what the regression should look like. As you're seeing the attributes of the IRIS dataset, which we are going to be very It's going to be used in machine learning. It's a very, very famous data set, and it's very classic. It is also a straightforward machine learning classification data set. As I was still talking about the parametric models, statistical models, and they make assumptions about the underlying distribution of the data. Yes. When we continue, we go to the K nearest neighbors algorithm. And this is an algorithm. This is an algorithm that calculates the distance between the training data and the test point. Okay, the way I understand the K nearest neighbors algorithm, this algorithm, for example, you want to identify what's the test of what do people take in a society on coffee. Is it tea? Is it coffee? You're going to just search the 3 neighbors around. If in those 3 there are 2 that take coffee, you're going to conclude that the whole society loves coffee more. So for the K nearest neighbors algorithm, for it looks for the closest data sets. Yes, so it makes decisions based on what is happening in the neighborhood. And we have the applications of the K nearest neighbors algorithms. That's that we have text mining, we have agriculture, we have finance, we have cargo competitions. Yes. When we continue, we look at the pros and cons of the KNN algorithm. And one is it is easy to implement, no assumptions about the data distribution. Yes, so it is easy to implement because remember you have moved around, and yes, so it works for regression and classification and suitable for multi-class problems. We go to the cons. Slower with larger data sets, skewed classes can dominate predictions, and sensitive to missing values and feature scaling. Yes. When we continue, we go to decision trees, and here we are looking at Gini impurity. This measures the frequency at which any element of the data set will be mislabeled when randomly labeled. The Gini impurity is calculated using a specific formula, and the Gini index has values inside the interval. Yes. When we go to post-pruning, sorry, it is also known as cost complexity pruning in a good approach. And it's really good. It is the attribute with a larger the decision trees are the following. So it is easy to implement and visualize. Yes, it is easy to implement and visualize. It has no assumptions about distribution because of non-parametric nature of the algorithm. Yes, so post-pruning, it is a technique used in decision trees, yes, and regression models to reduce complexity and preventing overfitting. That's what it basically does. And here I use the growing tree, yes, to train the decision tree or regression model on the training data. Yes. It has benefits because there is reduced overfitting, as I've told you, there's improved interpretability, and there is reduced computational costs. I think I should hand over to the next presenter. That's my partner, Magala Roni.
Thank you very much. I'm requesting Jocelyn to like her video. Do you mind? Yeah, I'll take you through ensemble learning. Ensemble learning, we shall talk about is a technique that combines multiple models. It's a technique that combines multiple models to create a single, stronger model that that improves performance and accuracy. Like in my simple term, what I can say about ensemble learning, for it combines prediction from multiple models to improve performance and robustness. It is often used to reduce errors, handle biases, and managing variance in predictions. Okay, according to what I know, for it combines multiple models, like, and improves its performance. For example, let me say that you are doing what, as Jocelyn has said, she has talked about everything about like the models, the decision trees, the random forest, everything concerning the models of machine learning. Let me say that you're imagining you want to predict the house prices. For a decision tree, you will you have to focus majorly on square footage. When you focus, in decision tree, you have to focus majorly on square footage. And for another model, like let me say linear regression or parametric models, any other model, you can emphasize so much on location. But for ensemble learning here, we shall combine both models to make a better prediction. That's my shortest understanding about ensemble learning. So here, in types of ensemble learning, we have the random forest, we have the boosting, we have the stacking. The random forest is the same as bagging, whereby bagging basically collects decorrelated decision trees, or like combines models trained a different subset of data. Yeah, that's how I understand bagging. Then boosting, for boosting here, I can say like sequentially trains models where each model corrects errors of the previous one. When we look here at the bootstrap, we only have a population sample, but we want to pick out information about the whole population. How do we make sure that this sample represents that population? Is the mean of a sample a good approximation for the means of the population given? That's how boosting works, or bootstrap. Going further, we have some of the cons and the pros of random forests. Some of the pros are robust to outliers. The random forests can robust to outliers. The random forests work well with non-linear data. The random forest lowers risk of overfitting, and the random forests run efficiently on a large data set. The cons then, the random forests are always biased while dealing with categorical data. They are slow in training. They are not suitable for linear methods, and when we apply the greedy algorithm, they do not yield the global optimum tree structure. We have differences of boosting and bagging. You can say that boosting, here we deal in sequential tree growing within a weighted sample. Like when we are to collect or combine data or get a data set of, when you're using boosting, like we deal majorly with sequential tree data, a sequential tree growth within a given area with a weighted sample. Then bagging, for it, we deal with a parallel tree growing area within a subsample. Going furthermore, we have the support vector. Support vector here, what I know about it, it's a supervised learning model used for classification and regression. It majorly finds the best hyperlane that separates the data into classes. The best hyperlane. Let me say that you have drawn a graph, but within that graph, we have mixed triangles, circles, triangles and circles. Yes, triangles and circles, or like, let me say, okay, giving a simple example, emails. Someone has sent emails. So giving, like, when you have drawn that graph, we have inserted in emails, but we don't know which. We want to separate the non-spam and from the spam. So we shall draw the line of best fit, which is the hyperplane, so that we separate majorly, like the downer part can go with the spam emails, and the upper part can go with the what? With a non-spam email. Yeah, to just classify emails. Here we see that it focuses majorly in maximizing the margin between classes while handling outliers. It transforms data into the kernel function transforms data into higher dimensions for separability, then defines similarity in transformed space. Going furthermore, we have the K-means clustering. Clustering, in a simple way, how I understand it, grouping, like clustering data, grouping data. Let me say in terms of groups, small groups. K-means here, clustering, is an unsupervised learning, whereby it deals so much with the data that is not labeled. It minimizes the distance between points within a cluster while maximizing the distance between clusters. Yeah, that's how I understand it. The algorithm steps that we can think of, choose the number of a cluster, like choose the number of groups K, initialize the K, centroid randomly, then assign each data point to the nearest centroid, then recalculate the centroids, yeah, in terms of cluster centers, based on current cluster members, then repeat until the cluster centers are stabilized. The strengths, we have it is simple and easy to understand and implement. Then it's considered as a linear algorithm. K-means is also most popular clustering algorithm. The weaknesses we have, it's only applicable if the mean is defined. Like, I think we know how to get the mean. We get the average. The K-means algorithm is sensitive to outliers. Then K-mean algorithm is also sensitive to initial seeds. Going furthermore, we have the PCA, which is the principal component analysis. Here, majorly focuses, it's a dimensionality reduction technique. For it reduces a dimension. It's a technique used in dimension reduction that transforms data into fewer dimensions while retaining as much as variance as possible. Yeah, for it will reduce the dimension of the data while keeping the information loss to a minimum. The steps that we can use are identify the directions, then project the data. Yes. Then an example that I can give, considering a data set like of 100 members or 100 features, PCA feature, okay, it will reduce the principal component analysis will reduce it to 2 features while preserving most of the information. Breaking it down, like let's imagine we have a 3D scatter plot. We are trying to build a 3D but scatter plot. Then PCA projects onto a